So, uh, so what's this about? I've been talking to people about continuous delivery for a long time now. My book was published sort of 10 years ago, and I've been helping people do it for longer than that. And one of the frequent comments that I get is, "Oh, yeah, that sounds really good. That's what we want. But you don't mean doing that for data, do you?" Well, actually, yes. And that's really what my talk is about today. I'm happy to take questions as we go through. I might have to, depending on how many there are, we'll see how that goes. And I will try and leave about half an hour at the end to make sure that we get into this in some detail. I've got probably slightly too many slides, but we'll see how we do with that as well. So what is continuous delivery? And I think that's a good starting point. And I think maybe, perhaps, not quite what you think. I think that what many people think about when they hear the phrase continuous delivery these days, in part because of Jez and I, is deployment automation. And it's way more than that. I think that what we're really trying to achieve is this. We're trying to optimize the software development delivery process from idea to getting working software into the hands of our users, and then gathering feedback so that we can learn quickly. And that's it. That's kind of really the scope of continuous delivery. Except what that means is that if we really want to take that idea seriously, that's pretty much the scope of all software development. So continuous delivery is an organizing strategy approach for virtually the whole of software development, in my mind. Now, I think of it as an engineering discipline, and it's deeply grounded in these kinds of ideas. We're going to try and strive to achieve a repeatable, reliable approach to delivering change into the hands of our users. And to be able to do that, we need to take control of the variables. We want to be able to do things repeatably and reliably. We can't just cross our fingers and hope that everything's going to work and say things like it works on my machine. We need to do stuff to minimize the variance. We want to make our systems and our processes more deterministic. If we run the same test every time we run it, we want the same results. If we deploy our software into production, every time we do that, we get the same results. What this leads to is a more experimental approach to software development. We're going to proceed as a series of small experiments. We're going to measure the behaviors, the results of those experiments, and as a result, we're in a position to make more evidence-based decisions. I think that if you put all of the words together on this screen, I hope that you will see that what I'm really talking about here is starting to apply the ideas of science and engineering in a pretty serious, profound way to the act of creating and delivering software to the hands of our users. And I think that's what we're talking about here. I think that continuous delivery is probably the best candidate that we have at the moment for something that we could consider to be a genuine first-class engineering, definitional terms kind of idea in terms of engineering discipline for software development. So one of the mechanisms that we use in continuous delivery is this. This is the idea of the deployment pipeline. And we're going to create a deployment pipeline, a mechanism that's going to evaluate our changes to our production systems and make them more repeatable and reliable. We're going to put all change to our production systems through the deployment pipeline so that we can get to that more deterministic result, and we're not going to be making excuses, well, it worked on my machine, as I said before. So if we want to do that, then we need to think very carefully. But one of the principal tools for controlling those variables and making things more reliable and repeatable is version control. And we want to version control the code that we create for sure, but everything else too. We don't want the configuration of our systems, the data structures that we deploy, the infrastructure that we depend on, any of those things to vary and so stop us being able to get a deterministic result. So we're going to version control pretty much everything. This is a list of principles that are in my continuous delivery book, mine and Jez's continuous delivery book. And this is repeating some of the things that I've already said, but we're aiming to try and create that more deterministic approach for releasing software. And that means we're going to automate pretty much everything and keep everything under version control. We're going to optimize to have fast feedback, to learn earlier in the cycle, and to focus on high quality work and build upon stuff that we know that works. But there's another take on this, and this is another quote from Jez and I, which is continuous delivery is the ability to get changes of all types, including new features, configuration changes, bug fixes and experiments into production or into the hands of our users safely and quickly in a sustainable way. I want to pause at this point. We advertise this talk as continuous delivery of data, and I haven't really mentioned data very much yet, and you might be thinking, what's he talking about? But I want to point out that I haven't mentioned code either. None of the stuff that I've talked about is about data or code. It's about all of the information that we deal with as software development. So all of these ideas that I've just spoken about are equally as valid for data as they are for anything else. If we want to be getting into the realms of an engineering approach, then we're going to be deterministic about data as well as everything else. So we want to version everything. We're going to make change in small steps so that we can kind of limit the blast radius if something bad does happen. Simplify each change so it's easier to reason about, easier to understand. We're going to test everything that we can think of pretty much, and we're going to use our desire to achieve all of those things to design for migration to allow us. We're going to treat all of these things seriously, and that's going to have an impact on the kinds of systems that we design. And this is one of the huge values of this engineering approach, is that when we do those kinds of things, we start to get other add-on benefits. If you start designing for things like testability and deployability, you also get as a side effect better separation of concerns, better modularity, better higher cohesion, all of this good stuff that we're striving for in the design of our systems. So we're going to version the code we create, and we're going to version everything else. So data needs versioning too. It doesn't really count as continuous delivery if we can't release because our schema has changed. And what does that mean really? What do we mean when we start talking about data? It's kind of all data really, but in this context, what we're thinking about is there's a difference between the data that is deployed at release time and that is generated through the action of the system, the transactional state that we generate during the function of our systems. And we need to think about both of those cases. The first class is probably slightly easier to understand. We got ideas like continuous integration, infrastructure as code, good configuration management, those sorts of ideas. But the other stuff is a bit more challenging. And then there are some grey areas. There's also stuff like reference data and runtime configuration. So I want to talk about all of those to some degree. I think there are a few different contexts that matter when we start thinking about data and continuous delivery. So there's the data in production, of course, but there's also the data that supports automated testing, and there's the data that supports manual testing and performance testing, migration testing, any kind of testing that we've got. And we want to think carefully about how we're going to deal with all of that stuff. When when we start thinking about this, I think that fundamentally, whatever we mean when we start talking about data, there's two different aspects to that. There are the records that we generate, that transactional output of our system, and the structure that matters for us to be able to interpret those records. And I'm going to continue talking in those terms, and that I'm probably going to be, depending, because it's the most common language that we can use to share meaning, I'm going to be referring to ideas in the terminology of relational databases. But I'd like just to point out that this is just as true if you've got a graph database or a column store or whatever other kind of form of data that you're dealing with. I once did some of the techniques that I'm going to describe today in the context of the in-memory state of a rich domain model for a trading system. And we had an event-based system, and we used the data migration techniques that I'm going to talk about on that system, even though it wasn't a conventional database. So do keep that in the back of your mind. The ideas that I'm describing are applicable pretty generally, I think. So let's start off thinking about the idea of being able to change the structure, the schema of the data that we're dealing with. Structure must be allowed to evolve if we are to have useful systems. One of the core tenets of agile thinking and continuous delivery is very much a kind of second generation agile approach. One of the core tenets there, though, is to be able to inspect and adapt, to be able to learn. You don't start out knowing all of the answers. And that means that we must allow ourselves the wiggle room to make a mistake and get something wrong in our first thoughts about what our design may be. So that means that we must allow structure to change. We must allow ourselves the freedom to try something out, find out that it's not quite what we wanted, and change our minds. There's a good quote from Fred Brooks. If you've not come across Fred Brooks is an old school software developer and computer scientist who wrote a book called The Mythical Man Month in 1970. And if you were to take my advice, you'd read that anyway, because that's a fantastic book. And even though it was written in 1970, my guarantee is that by the third page, you'll be nodding and smiling as you recognize that we're still doing it as wrong as they were then in many ways. The systems he was talking about are a bit different, but the rest is all the same. And one of the things that Fred said is, as soon as one freezes a design, it becomes obsolete. So if we want our designs to be living, live things, we've got to allow this freedom to discover new ideas and realize that our design isn't optimal. So we've got to allow structure to evolve. And as soon as we assume that, we've got to migrate data, because if the structure evolves, we need to be able to still be able to interpret the records that structure embodies. So we've got to think about migrating data. So how do we allow the structure to evolve? So the easiest way, the way that we're going to make our life easiest if we are going to allow that evolution, is to make additive changes. If we want to be able to step forward and step back to any version of our data in the history of our software, then we can't afford to lose information. And if we delete information, it's gone. So if we have a data migration that deletes old records, they're gone. We can't step back from that position. So if we want to be able to retain the ability to step back, making additive changes can make our life a lot easier. By which I mean, if you are have a computer science bent rather than just a practical programmer bent, in computer science terms, really what I'm talking about is kind of the flow of events. You treat your data stores as a record of the timeline, and then you just kind of surf the leading edge of the timeline, and you draw the line through your data at the point that makes sense to you. If I've got a relational database working in that kind of model, instead of deleting a record, I'm going to leave the record where it is, but mark it as deleted and then ignore it from now on. So I kind of treat my data store as a stream of events, and kind of that's one way in which we can make changes, which is useful. And with the modern capacities for data stores, not extravagant. So that's kind of fine. So if we want to, in addition to that, we want to version control everything. So we're going to version control, DDL scripts, migration scripts, Delta scripts, tests of those things, everything. And we're going to think about database refactoring techniques. What are the patterns? What's the advice to carry out certain kinds of changes in database? And there's a great book on that topic, which I'll mention as we go through it. So let's get into the detail of thinking about versioning schema change. Schema version. So my advice is that first of all is to absolutely version the schema. Have a unique ID. Have a sequence number for your schema. And a monotonically increasing sequence number is ideal, because then you can see where the gaps are. If I say my database is at version 17 and my release candidate requires version 20, I know that I've got to apply changes 18, 19 and 20 to get it there. And so having a monotonically increasing sequence number is a good tool for that kind of thing. So once we've got this version number, store the schema version that the app can work with the application. So the application knows that it works with this particular version of the schema. Also store the schema along with the data. So maybe you have a schema version table in your database, or a header entry or something, but somewhere where you can go and inspect, a well-known place where you can go and inspect the data and know which version that data is at. And then you can decide whatever it is that you need to do next in order to be able to translate it from one version to another. So let's imagine we've got a system of some kind and it's got a data store of some kind. There's a relationship between the two. And that relationship is important, because if the relationship drifts too far apart, they can't talk to one another. So if we've got to maintain that somehow, we need to understand that a particular version of the application works with a particular version of the schema. We need to know that, and so we need a record somewhere that tells us that. We need something that says this version of the application works with this version of the schema, and this version of the application works with this other version of the schema. And we need to maintain that record somewhere so that we can automate the management of the two. We can ensure that when we deploy an application, the data is in the right shape for it to be able to interact with. The easiest way to do that, by far the simplest way to do that, is to bung them all into one big repo. Keep them together, and then you don't have any dependency management problem. You don't have to do anything smart. All you do is that the current version, any given version, any given configuration set in your version control system is going to work together. The data and the application are going to work together. That's by far the simplest way of doing things. You can do other things, but you're just making life harder when you do. The caveat, I suppose, here is where you have shared schemas and different applications working at different versions, and then you've got to get into dependency management territory, and that is automatically going to make your life more difficult. But if you can possibly get away with it, put them all together into one big version control system. And then we're going to have a series of versions of the application and a series of versions of a matching series of versions of the database schema, the data schema. And so we're no longer talking about schema versioning. We're starting to talk about data versioning. We can also think about the records that populate that schema. And those are different. We've got to think about those separately. It's a different kind of problem, but it's related, and it's starting to get a little bit more tractable as we start to be a little bit more disciplined in the way in which we manage the versions for the application and the schema. And don't worry, we're not going to skip over that. We're going to talk about that. So here's my application and my data, my data store. And when we make a change, we're going to change the application and we're going to change the data store together. Whatever it takes to make something work. If I'm going to make a change to the data store that requires a change to the application, I do them pretty much in the same commit. Well, no, I do them in the same commit, and then I'll keep everything working all of the time. And then what I'm going to do is that I'm going to record the change to the data store as a little delta. I'm going to write a script that says, in order to move from, in this case, presumably version number 75 of the schema to version number 76, these are the steps that you take. And I'm going to encode that, and that's what I'm going to version control. And then we can start thinking about tools that can support us playing some of these little scripts. We're going to put all of these together in one version control system to make our lives easier too. So now we're going to make a series of changes to our data, and for each change we're going to create a Delta script and record that Delta script and keep the collection of them. We don't necessarily have to be releasing every one of these changes. We can release at any point, which is one of the tenets of continuous delivery. Our goal in continuous delivery is to work so that our software is always in a releasable state. So every single time that we make a commit that changes the data structure that we deal with, we commit stuff that's going to keep everything working. And that includes writing one of these little Delta scripts. And we version them all together into a version control system. So what does one of those Delta scripts look like? So we're going to have the schema changed, the thing that describes the way in which the data structure changes. We're going to have something that tells us that in order to be able, so if we've got any records in the previous version of the schema, this is what it takes to move those to be the right shape for the new version of the schema. Little migration scripts. And if you follow my advice, you're also going to have a little automated test that validates that those migration scripts do what you think they do. And guess what? We're going to version all of those things together and put them all into the same version control system. So now we can think about deployment time. So okay, so let's think about deploying this stuff. We've got all of this stuff in version control, and we want to be able to deploy. Let's say we want to deploy to a test environment. Remember what I said earlier, within our data store, we've got a record of what version of the schema it is at. So it's got a little table, and it says that the current version is version 79. And at the point at which we come to deploy the version of the software at the top of the screen, that requires a data store that's at version 80. So deployment tools go and look in the data, in the release candidate, the deployable software, and say, okay, this release candidate needs version 80. They go and look in the data store and say, this data store is at version 79. Therefore, we need to play the script for 80 and migrate the data. And bingo, you've got the data to the new version in your test environment. Similarly, your production environment, that might lag a little bit further behind because you're not releasing quite as frequently as you are to your test environment, and you come to deploy there, and it says, okay, our release candidate needs version 80, the production database is at 76, Therefore, we need to play 77, 78, 79, and 80 to get it to the right version. We play those scripts in order, in sequence, and we've got our database at the right level now to work with the application. This is pretty powerful. This is pretty flexible. There's one more refinement that you can do that's common. Instead of just writing one script at the point at which we make any change to our data, we could write two. We could write one that moves us from the previous version to the current one, and one that moves us from the current one back to the previous version. If we haven't lost any data in any migrations, then that should work. We should be able to do that. And if we were able to do that, what that would mean was that we can now deploy any version of our application to any version of the infrastructure and migrate the data in any direction. So we can deploy any application at any time and keep everything working. So in my example, we've got a version 81. We're going to roll back to version 80 and play the undo script and get the data store back to version 80. So now we have complete flexibility to be able to migrate in any direction. This is extremely powerful. There's a couple of tool sets that I will point you in the direction of. There's the open source one is called Flyway. It's written by Boxfuse, but I think that Redgate have taken this over now. So actually, these are both Redgate things. I don't have any connection to either organization, so it's honest advice. Flyway's pretty good. I think they've had over 40 million downloads. It's a pretty successful open source project. All it does is what I've just described. It manages the scripts for you. It will do the versioning and all that kind of thing, and then it will pick, based on some naming convention, it will pick the appropriate scripts that need to be played to get a version of the database into a particular state. One more thing to say about that migration strategy is that the rollback scripts, my experience is that most people that start out with this kind of migration strategy absolutely want the rollback scripts. And then after they've been operating it for a little while, they start to get a bit nervous that they almost never, if they're only good at continuous delivery, they almost never roll back. And so, because you just roll forward instead. And so they tend to drop the rollback scripts after a bit because they're nervous because they haven't run them and they don't know that they work. But it's a good insurance. And I've been through that. I've been through that exercise a few times on different projects myself. So we're now starting to get into the territory of things that we might think of as kind of data migration patterns. There's a variety of these. The thing that we've just been through is a data migration pattern in its own right, and it's what I would call a deployment time migration. So that pattern that we've just described, this is what you do at deployment time. You make that happen as part of the deployment of your application always, and so if there are any migrations that are required, it will apply them by default when you deploy the system, and that's great. But there are times when that's not enough. There are times when the data set's too large, or you don't want downtime with your application and all of those kinds of things. And that gets you into a different collection of patterns that are of interest. And so I've just pulled a few together to talk about. So the first one's what I call lazy reader. So the system can always read old versions of the data, always. Every single record is individually versioned. So every record has a version number associated with it. And when a record is accessed, the system at runtime selects an appropriate reader to translate that version of the record into the current usable system view of the world. The The reader presents a consistent, up-to-date interface to the system, whatever the internal data structure. This is best implemented using a kind of strategy pattern for the readers, and you use the schema version of the data as the key to identify which reader to use. The best use case for this is with very, very large data sets. If you've got humongous data sets, this is perfect, because if you've got terabytes or petabytes of data, you can't afford to go and translate those. You can't afford to go and rewrite those. I once worked on building a trading system. We built a financial exchange, and the financial exchange processed 1.3 times the daily volume of Twitter in data. And most of the data is really dull and boring, but you have to keep it for 7 years. So we were generating, it wasn't quite this, but it was roughly a terabyte a week of data that we had to archive. You can't afford to go and rewrite a terabyte a week. It's just insane to even think about it. So you need a strategy like this. You need to be able to dynamically, so we just wrote the data, and the beginning of the stream of data, you know, was written with the old version of the schema, and the newest record was written out with a new version of the schema. But we could read any of them. We could read any version. This is good for hot deployment, because you can imagine, you know, if you change the version of the schema that writes, your application writes out something new, you deploy that and you update all of the other readers to do the translation into your current model, and you know, whatever you deploy is self-consistent, whatever the nature of the data. It's scalable. It can cope with vast amounts of data. The translation cost is on every read, and so it's spread out over time, and therefore is in effect free. The downside, it adds runtime complexity. If this idea scares you, that's good, because you've understood the problem. We're going to have this ever-growing collection of readers, and every time we change our internal representation, we've got to go back and we've got to change all of the readers. So it's a maintenance burden. It's a significant overhead that we've got to stay on top of to keep all of the translators working. And in this model, you don't even try to ever achieve data consistency. The consistency is in the application's view of the data, not in the data itself. The data is never going to be rewritten. The next in my strategies is the idea of the lazy migrator. The system can read old versions, and this time it writes out new. So when it comes across an old version of the data, it's going to read it as the old version and actively write it out, translate it to the new version. Each record, again, is versioned. When a record is accessed, we pick a suitable migrator, and that is used to read in the old version of the record and translate it, write it out in its new form. This is, again, best implemented as a strategy pattern and using the schema version to identify the appropriate strategy. The best use cases for this: hot deployments, large data sets, pretty extensive data sets. It works at fairly large scales, perhaps not quite as large as the previous one. It's good for hot deployment because we can, you know, when we deploy, it's going to be able to read old versions of the data, and as long as we've got the migrators in place, we're good to go. It's scalable. Translation cost is on every read, and again, so it's spread out over time. And migrations can be chained together. So you can imagine having a migrator that goes from version 1 to version 2, and then another one that goes from version 2 to version 3. And as long as you do them sequentially, everything's going to work fine. The system is eventually consistent with respect to data. You can't tell when all of the translations will have happened, but at some point you assume that they will. You know, as long as you access every record in the database, at some point in the future, every record in the database will be translated. Again, it adds runtime complexity. The other downside is it's not clear when migration is finished, when you are done, because it's kind of a drip feed as you're just reading data, and it's driven on demand. When people ask for data, that's when you'll translate it. The maintenance overhead is similar on a similar kind of scale to the lazy reader, in that we've got to maintain this collection of migrators. The slight caveat there is that because we can chain these things together, each migrator, we don't quite have the maintenance burden to always bring everything up to date to the latest version of the application's understanding. So that's a slight benefit. Next is the downtime migrator. So again, the system can read old versions and write out new, but this time we're going to change the way that we organize that. Each record is versioned again, but now old records are actively searched for and migrated when the system is idle. During downtime of the system, we go and scavenge and see if we can find anything that's out of date, and we're going to translate that behind the scenes. This is good for hot deployment and medium to largish data sets. I'll explain what I mean by that in a minute. The advantage of this, hot deployment, scalable, because the translation cost is in downtime. You can discard translators once all of the records of if you do a scavenge run and you can't find any records in an old version, at that point you could throw away that translator. The system's eventually consistent with respect to data, and you can chain the migrations together again as before. Runtime complexity, and this may be inappropriate for vast data sets. Time is finite. There's only so much time, and there's only so much idle time. If you use up all of the idle time doing translations because your data set is so huge, then this isn't going to work for you. So this isn't quite as scalable as the other two, but it's pretty good. You can do this with some pretty large data sets, and it's going to work okay. The last one to mention is the one that we've already mentioned, the deployment time migrator. On deployment, the system migrates all records. The advantage of this, and it's a big advantage, the reason why I started with it is because it's simple to understand. It's kind of obvious that at the point at which we deploy the software that requires a new version of the data, that's a good time to migrate. That's pretty good. It can be implemented either as a startup behavior of the system itself. The system is responsible for its own migration, or we can treat this as an independent process, but that's managed by the deployment tool. So at the point at which we deploy, we go and inspect the release candidate, the deployable thing, to see what version it needs, and then we apply any migrations that are required. The downside of this is it's a little bit tricky to test. We're tempted to test the data itself and the migrations. It can be slow if you've got very large data sets. It can take a long time to do some of these migrations. I had a client recently that was very nervous because they were running out of time, literally. When they deployed, their software was deployed by field representatives. They have an army of people in vans going and delivering software to, in this case, hospitals, and they would go and they would deploy the software. But the cost of migration was so large that they were running out of time, so that they couldn't do it in a single day. It took more than a day to migrate the data, and that was becoming a problem. So this is a downside of deployment time migration. It requires application downtime. You can't really it doesn't make sense to be migrating data while the app's live, creating new old records, because when are you going to translate those new old records? How are you going to deal with those? So it's not ideal for kind of frequent continuous delivery style deployments. Let's think about testing these migrations. I think it's a fairly common mistake to focus testing for data migration on the state that the database ends up in. And I think that's probably a mistake. I think that gets you into complicated territory about what that means and narrows your focus to testing only a small set of cases. I think a better focus for testing these sorts of things is to kind of take a data migration unit testing approach. So instead, focus your testing on validating that the migration script for your data or your migrator does what you think it does, and test that. So take a kind of test-driven approach to data migration. And I think that's by far the better way of doing these and evaluating these. Largely using synthetic data, it means you can get more interesting cases that you validate in your testing to check that it works. Migration testing is a little bit different to regular unit testing though, and I would recommend that you include migration testing as part of your continuous integration stage in your deployment pipeline, so that at the point at which you commit, you're going to run all of the migration tests alongside any other unit tests, so you get fast feedback and you know that your migration scripts do what you think that they do. But one of the key differences here is that you care about the order for these things. For regular unit tests, you don't care what order they work in, but for this you do. So the pattern is that you check out a particular version, you apply the migration of that version, you test the migration, and then you apply the next migration, then you test that, and then you apply the next migration and you test that, and so on, because they're additive and you build them up in order if you're going to do that kind of testing. There's another aspect to data beyond just migration and thinking about data in the context of continuous delivery, and that's really about managing data in tests. We'd like to be able to run our tests anywhere, and the best way to achieve that is to ensure that our system is in a fairly neutral state. By that I mean largely empty of data. We'd like to be able to deploy it with nothing there and then generate the data during the course of the testing. I think when we start following this line of reasoning, we start, I think there are three obvious different categories of data that are worth thinking about, and we've kind of touched on these briefly already. The first one has been our focus so far, really, transactional data, the data that is generated during the operation of our systems. The next is kind of reference data, and this is sort of the lookup data, postcodes or zip codes or symbol tables, that kind of stuff, and that has the interesting characteristic, the useful characteristic, that it's read-only. It's kind of lookup data that we're not going to write back to. We're not going to change. And the last one is kind of configuration data. That is data that does something to define or parameterize the behavior of our system in some way. And then we could think of these three different strategies. So we could choose to use production data. We could generate data in the scope of a test and use targeted synthetic data, or we could use what I call versioned data, which is you can imagine your deployment tools doing something like, okay, I'm deploying to an acceptance test environment, and therefore I need to deploy this set of data to support those tests. You can imagine doing that kind of thing. That's what I mean by versioned data. So let's go through each of these different three classes of data and see which of those strategies works best. So I don't want to use production data for testing transactional behaviors. I see this quite a lot in clients that have kind of a reasonably, if you'll forgive me, old-fashioned take on automated testing. They'll just throw production data at their system. And okay, that might be better than doing nothing, but it's not much better than doing nothing. It doesn't really get you to evaluate the interesting cases. You can't kind of try the corner cases and find out what happens if this weird thing happens. And that's usually where our software screws up. So that's really the interesting cases. So we don't want to use production data. It's too big, it's too unwieldy, and it's not targeted enough for us to be able to do good tests. So we prefer to generate these in the scope of the tests. At the time that we write an individual test, that test as a set of data that must be in place to get the system into the state that we want it in. And so we're going to do that. Last, we don't want to use version to test data because, again, that's too generic. It means that it's likely to be shared between test cases, and that's a danger because it means that we're going to then leak information between tests, and we're going to compromise the repeatability of our test cases. I want to be able to run any test over and over again and get the same results every time. And that means the simplest, best way of doing that is to generate in the scope of a test. Next, reference data. Again, I don't want to use production data. Reference data for a production system is usually large. If we've got a lookup table of postcodes or zip codes, it's probably in the millions. And so I don't want to be deploying millions of records for a test. Mostly, I'm just going to generate it in the scope of the test. I'm going to fake the reference data some way and generate it in the scope of the test. There might be some utility to using versioned data for this. Because it's read-only, we can use that advantage. So instead of having lookup data with millions of records, we could, a postcode lookup with millions of records. We could just have 50 records in our postcode table or something like that. We could do that kind of thing. So maybe use version test data, but my preference would still be to generate it in the scope of the test, and then you can target exactly what you want. Configuration data is interesting though. That's kind of the opposite of transactional data. For this, my preference by a long way is to have the production configuration be the default configuration of the system. If I configure my system in a test environment and use the same configuration as I will in production, that means I can test the configuration. If I've got some dramatically fake version of the configuration in a test environment, then I don't know whether my system's going to work in production. So that gives me a big power. So I much prefer to use the production configuration for any testing. Now, there may be some unusual kinds of tests, really testing the range of configurability that I might want to do, and so I might want to generate some of these things within the scope of a test, but that's a fairly unusual corner case. And there are certainly going to be some things that I don't want to use the production version. I don't want to be writing test data into a production database. So I'd like to use a different, point to a different data store in my test. So some versioned test data is a good idea, some overrides. So my preferred approach is that you have production configuration by default, and then you override the sensitive bits, any secrets, any passwords or anything like that, or any stores that use a different messaging system or a different database to the production version, that kind of thing. I'm going to whiz through this. So what about machine learning? Because that's really different, right? That's a different kind of thing. And I don't know how many people on the call are interested in machine learning. Maybe some. And I should say very clearly, I am not a machine learning expert. But I've been involved in a few interesting conversations with some people that are. I think there's some ideas that are worth thinking about. There's some relatively complicated pictures in this that I'm going to whiz through quite quickly, but just try and put the ideas in front of you. Machine learning models have a shelf life. They are going to go out of date, and so to be able to keep them up to date and to change things with control is kind of fundamental. And being able to do that efficiently is important. People doing sophisticated things with machine learning will often take weeks, months, sometimes even years training algorithms and going through the iterations to train things. That sounds an awful lot like where we were in more regular software development a decade or so ago, where we were, waiting a very long time to find out whether our stuff worked. That's generally a bad idea. So I think that in many ways, continuous delivery is even more important for these sorts of things than it is for regular systems. This is a quote from Emily Korsinski, who's one of the people that I've been talking to about some of this stuff. She's data scientist for ThoughtWorks, and continuous delivery for machine learning is about transitioning from research into production states. So it's important to be able to do that reliably, repeatably, efficiently. The normal kind of pattern of what's going on with machine learning is something like this. We're going to have some desired results, some target that we're going to try and achieve, and we're going to throw some training data at it, and we're going to train the algorithm in order to be able to generate a model, at which point we'd like to be able to deploy that model into production and have it operate on live data and make predictions and results. In reality, it's a bit more complicated than that, and there's these kind of breakdowns of what's going on. There's kind of the data acquisition and preparation in terms of getting ready for training, sort of allocating, trying to figure out what data to use to train our models and what targets to aim it at, and then experimentation as we do the model development and the training itself. And there's a feedback loop to establish to evaluate the accuracy of our training and whether that works or not, and whether we need to think about fixing the data that we are using for either our target or for our training data. And then ultimately, if we get to some desired level of accuracy with that training loop, then we're going to go out into production and deploy this into production. And again, we need to be monitoring that and understanding whether the accuracy is being maintained in production or whether it started spouting fascist rants like the Google thing did, and we need to pull it. We need to understand whether that's going on. So this model is kind of interesting. What could we think of doing for these kinds of things? Well, obviously, we want to version control the training data and the desired result and the targets, and also the models that we generate. We want to know which version of the model, and we want to manage that stuff. And strangely, this isn't always obvious to people that are doing machine learning, but this is obvious if we think about this in the context of more regular software development. And then we want to manage the environments in which things work. Things like ideas like infrastructure as code to make sure that those environments are repeatable and reliable and are going to work effectively. So we can apply that kind of thinking too. We could think about where to add this. So we can use version control for model development and infrastructure as code for the training environment, and version control for the data acquisition and combination for the data prep, infrastructure as code for all of these environments, and so on. And so we can start to see that this problem is not very different in many aspects. Now, the problem is that it's not that we don't want repeatability and determinism. I think from my perspective, and remember what I said at the beginning, my caveat is that I'm not a machine learning expert, but from my perspective, there is no real difference in this respect between a machine learning system and any other. The way in which we generate the model, the code that we want to execute in production, that process is a little different, but we still want that to be repeatable. We still want that to be reliable. Given the same sets of inputs, we'd like to be able to get the same sets of outputs. We'd like to get all of that information as quickly and as efficiently as we possibly can, so we can establish clean feedback loops so that we can learn more efficiently. I think that means that we need deployment pipelines. We need to think about how to create a deployment pipeline for machine learning. How do we manage this, regularize this so that it works? So what's a release candidate mean for machine learning? Well, for conventional systems, a release candidate is a working deployable system. I think for machine learning, a release candidate is a working deployable model, including the monitoring and alerting associated with that model. It's really not very different. So is there a version of a deployment pipeline that we could think of applying for machine learning systems? And my caveat before I show you this is that we're not there yet, but some first thoughts, some starting points. So we could think about version control and artifact repository for managing the information that we're going to deal with. That's a surprise. That's not what lots of people do. Lots of people doing data scientists don't even take that step. So that's a good step forwards. We want to be able to have discoverable and accessible data. We'd like to be able to have the stuff, our training materials and our targets really usefully version controlled. And we want to have the infrastructure for environments and experiments repeatable and use infrastructure as code techniques to be able to do that. We want to be able to encode model performance and assessment tracking. We don't want that to be ad hoc. We want to think about that, design it, use engineering principles to be able to collect that information. And we want to have model monitoring and observability in production so that we can learn from these things. The best way to test model performance is to see how it performs with real-world data. So in an ideal world, what machine learning practitioners should be doing is taking small steps, doing the training, get the training, understand the training, then get the model out, see how it works, monitor it, figure that out, and be able to round trip that, be able to go around and do that over again. And that would be a more effective way of working. We should be thinking about doing things like deploying multiple models in production and comparing the results between different models in production with real-world data. And that's what we would call A/B testing in other scenarios, and continuous delivery is kind of table stakes for that kind of thing. We need that kind of regularity and maintenance to be able to do this. That's my talk. That's the content of my presentation. I've overrun by a few minutes, but we've got time for questions. So if there are any questions, I'd be very happy to take them. I'll point you to my links. I've got a blog site. You can follow me on Twitter, and have some good conversations on Twitter. We've been doing some conversation starters and having some good chats on Twitter of late. And I have a YouTube channel where I talk about continuous delivery and lots of other stuff.